Dr. Pradeep Kumar Thapliyal from Atmospheric and Oceanic Sciences Group, Space Applications Center, Ahmedabad. Atmospheric parameters from Indian Geostationary Satellites for assimilation in NWP model.
I am Pradeep Thapliyal from Space Applications Center, Ahmedabad, and I will be presenting this atmospheric parameters from Indian satellites for assimilation in numerical weather prediction model. The original title I had given is from Geostationary Satellite, but I thought I'll also cover some of other Indian satellites like polar orbiting satellites which we are going to launch or which we are having at present in orbit. So a little modification here. Now I myself do not work on data assimilation as such, but I work on the first part of it, that is the data. That is we provide the data for assimilation in numerical weather prediction model, and that's what I will be presenting here. So these are the data requirements for the numerical weather prediction system. That is well known that the numerical weather prediction is an initial value problem. Of course, at a longer time scale, it's also a boundary value problem. And these this forecast from these NWP models largely depend upon the quality of the initial conditions. If you have better initial conditions, so your forecast will also have a better quality. So these are basically, these initial conditions are provided by the analysis. And these analyses are generated from the observations and the combination of observations and the model forecast. And observation comes from conventional data as well as satellite and radars. So in this one, this is the basic process of data assimilation process where we combine the observation and forecast. That is the first guess, and we compare these two and then decide the first initial state of the atmosphere that goes as the initial condition. And these are the basic example of conventional data coverage for atmospheric and oceanic observation. If you see these synoptic, land observations, surface observations, so they are mostly over land regions. We have some of the SIP measurements as well as some of the observatories over islands, but they measure only the parameters over land. Then we have upper air observations. These are the buoys over ocean. These are the upper air observations, and they are the observations taken from the aircraft. So you can see that these observations are not covering the entire globe simultaneously. So we have to go for some alternate source to provide these atmospheric informations. So basically, satellite has provided a better tool for to provide these observations over land, ocean, and three-dimensional structure of the atmosphere simultaneously. We have many satellites from international missions, and these data are now widely used in the numerical weather prediction model for data assimilation. And we have highlighted these Indian satellites here: Kalpana, INSAT-3D, then OceanSat-2. Kalpana, INSAT-3D, and OceanSat. Other satellites are the international missions. So I will focus mostly on Indian satellite data. So first of all, whether if you want to see the impact of satellite data for numerical weather prediction model, so first of all, whether we have to see whether this data is having any impact. So this is some ECM developed study where after control, and if we see, if you remove satellite data, we see that the predictability, if you include this satellite data, this is the forecast day, and if you see that this predictability, the 60% improvement, if you do not use satellite data, we can forecast only up to 5 days, and if you use satellite data in combination with other conventional observations, the predictability increases the number of days. So basically, for assimilation, you need two types of observations. One is observation as such, like temperature, humidity, wind, sea surface temperature, and many more parameters, which we are observing from conventional data. Either these parameters or recently now radiances are being directly assimilated into the model. So either you can retrieve these parameters from satellite observations, or you can provide radiance directly to the numerical weather prediction model to assimilate into that. And for radiance assimilation, this is basic flowchart for the data assimilation. Here, you have the satellite observations. These are the model fields. You compare these two from satellite as well as the forecast, and then minimize the difference between these two. If you have this measurement of temperature profile, humidity profile, or any other conventional sources, then that is the traditional way of assimilation. But if you use direct radiance for assimilation, then that is the radiance assimilation. In this one, we need a few more steps like bias correction, because radiance, satellite radiances and the radiances which are simulated from forward model by using first guess from model fields, they may have some bias. So you have to do some bias correction in this one. And then you need a forward model operator here so that you can convert model fields of temperature, humidity profile into the satellite equivalent radiances. Then compare these radiances and minimize the error between these two. So this way you can directly assimilate radiances. And why this radiance assimilation is popular? Because it reduces the time, because you are directly assimilating the radiance into the numerical weather prediction system. So you are not first retrieving the temperature, humidity profile, or other parameters from satellite observation, and then assimilating those into the model. So that way you are also reducing the error which will take place in the process of retrieval, as well as the time, because there it will the time will be double. So I will not go much into detail of these radiance assimilation. I will directly come to the my talk, that is the data availability from Indian satellite systems, geostationary as well as low Earth orbiting satellites. So currently we have in geostationary orbit Kalpana, INSAT-3D providing the data, and then in near future, like next year, we have planned to launch the INSAT-3D in orbit, which will have a sounder, which is very similar to American satellite GOES. And then we have polar orbiting satellites, OceanSat-1, 2, Saral. These two are the future satellites. So I'll explain in detail what are the parameters available from these satellites. So first I will start from geostationary satellites. So India started this Earth observations for atmosphere from geostationary satellite called INSAT series of satellites. And we are doing this observation for last 3 decades. So INSAT-1, INSAT-2 series, and then INSAT-2E was launched in 1999, and then Kalpana in 2002, INSAT-3A in 2003, and then we have planned for INSAT-3D in next year. So what are the basic observations from these satellites? We started from basically simple observation of clouds, because INSAT-1 series of satellites had only visible channel and one infrared channel in visible and infrared, thermal infrared band, with the resolution of roughly 3 km and 11 km. And they were basically providing the observation of the cloud fields, cloudy or non-cloudy fields. And the parameters, which were the major application from these satellites, were monitoring cyclone and monsoons, cloud motion winds, OLR, and rainfall estimates. So these were the basic parameters which we were deriving from INSAT-1 series of satellites. And this is the few sample pictures of INSAT satellite. So you can study the onset when you see the last cloud mass sitting just over the south of the Kerala. So this is the onset phase. This is the active phase when the entire India is covered with the clouds, and then this is the break phase when there are no clouds in the Indian region. So we could monitor the progress of the monsoon over Indian region from infrared and visible channels, as well as we can monitor the cyclone from this type of satellites, daytime as well as nighttime from infrared sensor. So most of these satellites were mostly providing qualitative informations. So INSAT-2 series had one new band, water vapor band, added in INSAT-2E satellite, that is from 5 to 7.1 micrometer. So we had now three bands in VHRR, that is in visible, infrared, and water vapor absorption band, and a new sensor called CCD, charge coupled devices, with the 1 kilometer resolution. So that is basically to monitor the mesoscale systems over Indian region. So these are the basic applications. So few applications were added from INSAT-1, that is the water vapor winds, that is the winds over upper troposphere that come from water vapor bands, and upper tropospheric humidity, and few more applications like mesoscale features that come from CCD bands. So these are the bands which we had in INSAT-2E, VHRR, one additional band here, water vapor. So resolution was 2 km and 8 km in infrared. And these are INSAT-3 CCD. These are basically working in the solar spectrum. So we can get these images only during daytime, not in the night time. So these are the few sample imagery. This is an additional that you have seen that water vapor, thermal infrared and water visible imagery. This is water vapor imagery, and basically this from this we monitor the water vapor fields in the upper troposphere, basically from 500 millibar to 200 millibar. And these are the CCD pictures. So CCD pictures, some additional features you can see is from sphere band, because if you see in the visible band here, you see this bright cloud patch, but over this bright cloud patch, there may be the ice cloud. So ice cloud you are not able to monitor from either from visible or from thermal infrared. So sphere band helps in detection of the cirrus clouds. You can see here brown patches here sitting over this white cloud. So this was additional information provided by this sphere band. And you can also monitor fog because it has a 1 kilometer resolution. So various applications were added in INSAT-2E. Now I will come to the present and future INSAT satellite series. Right now we have Kalpana at 74 east, this geostationary orbit, and INSAT-3A at 93.5. And future we are going to, next year INSAT-3D that will be placed somewhere in 83, 84. That is not yet decided. It will be around in this location. INSAT-3A and Kalpana, they have the same bands in the VHRR, except for INSAT-3A, which has additionally which has CCD also on board that, and other features remain same for visible, infrared, and water vapor channels. And these imagery you have already seen from earlier pictures. Now I will come to the products, the basic products which are available for numerical weather prediction as for data assimilation. And the most important parameter from these INSAT series of satellites are cloud motion vectors from thermal infrared band, and water vapor wind tracer vector, water vapor vector from water vapor channel. So this is the thermal infrared channel. So you will see wherever you find cloud tracer, cloud patches. So by monitoring the movement of these cloud tracers in half an hour imagery, you can see the displacement. By the displacement, you can find out the velocity of the wind at that level where the cloud is existing. But in this one, you will find that where you don't have clouds, you will not get any cloud motion vector. You will not get wind information. And also the wind information is only over that level where you have the cloud. It will not give complete 3-dimensional structure of that. So when water vapor channel was added, now water vapor channel, you have a complete water vapor field over 500 to 300 millibar level. If you monitor the motion, half-hour imagery of water vapor picture, you will find movements in the cloud tracers. These are the water vapor fields. So if you monitor the gradient of the water vapor fields, you can find out the water vapor tracers. So you get much more tracers or much more the wind vectors from water vapor wind than you are getting from thermal infrared channels. The total radiation measured from 4 micron to 100 micron. But we have a few satellites in orbit like RB, ERBS, which measure this radiation, upward radiation from 4 to 100 micron. But they are very few. They are scientific missions, and they will not cover entire globe and entire time. But if you have geostationary satellite, it can measure every half an hour. It can measure outgoing long wave radiation. If we can convert narrowband radiances, that is thermal infrared radiances, into the broadband radiances. So this is what we have done here based on radiative transfer simulation. We first developed a relation between satellite narrowband to the broadband, that is the OLR, using diverse profile data set. And using that relationship, now we compute the outgoing long wave radiation from Kalpana or INSAT water vapor and thermal infrared channels. And we compare that OLR with the other source of OLR from Meteosat and other available data sets. We find that Kalpana OLR products are very good. It is having RMS error of the order of 5 watt per meter square. So very good accuracy here. So this product can be used for climate research, as well as a very important diagnostic parameter in the model, NWP model, because in NWP model, the big problem is how to validate the cloudiness, cloud simulation. So as direct, you will not get any product. But OLR is an integrated effect of cloudiness. Okay, so if you compute OLR from your model and compare that with the satellite model, you will come to know where your cloud simulation is, whether that has some discrepancy or not. So this is very good diagnostic parameter for NWP model. Now next, this is the net short wave radiation. This is what I was discussing. So now from INSAT thermal radiances, we computed OLR. And this is one step further. From OLR, we computed short wave radiation. This short wave radiation is computed only over warm pool regions of ocean, where OLR is a proxy of convection, where in the warm pool we have convection, and due to convection we have this cloudiness, and cloudiness is indicated by the OLR. If OLR is very low, it means there is presence of deep cloud, so short wave will be low. So we developed a relationship between OLR, daily average OLR, and short wave radiation, which was computed from buoy measurements. Okay, so we took some buoy over this Bay of Bengal, this region here, some 7-8 observations of buoy over past 10 years, and then developed a relationship between 10 years of OLR product, which we derived from Meteosat satellite, and buoy observed short wave radiation, and then developed a relationship, an algorithm. And this our algorithm gives the best result compared to the other conventional short wave radiation product. So this red one is the algorithm which we developed at SAC. So these are the RMS error. So for the entire range of short wave radiation, that is, this represents a cloudy condition when short wave radiation is very small. This represents a condition when clouds are not there, when short wave radiation is very high. So entire range of short wave radiation, our algorithm performs best, and the next best is GVEX, which involves a lot of radio transfer computation and cloud data taken from ISCCP cloud product. And that data, the other data set like GVEX and ISCCP, that is not available in real time, that is available only up to 2008, whereas our algorithm can give short wave radiation on a daily basis. Today's this short wave radiation we can compute at 7 p.m. today, because we need OLR observation only up to 6 p.m. So that is the advantage of this, and this is a sample of net short wave radiation over Indian region from Kalpana. And here you can see the time series. This is a Julian day for 1 year. We compared short wave radiation between buoy. So this red line is buoy, blue is different products, and red. Okay, sorry, different. So first one is SAC, our algorithm versus buoy. Second one is GVEX versus buoy. Third one is ISCCP versus buoy, and last one is NSEP versus buoy. You can see that our algorithm works the best. Next best is the GVEX one. So GVEX and SAC algorithm, they work quite close. But advantage of our algorithm is that the data is available in real time, whereas GVEX gives you data 2 years back. And these are the impact study. If you use these type of satellite products for ocean model, this is just I'm showing some sample study of the ocean general circulation model. So our colleagues did this experiment when they forced ocean model with NSEP derived short wave radiation, and then they computed the correlation between SST simulated from that experiment with TMI SST. So they found that the correlations were very, very poor over most of the regions. Correlations were less than 0.5. And when they used this satellite derived short wave radiation into the ocean model, general circulation model, they found that correlation has improved. So SST simulation became better when you use improved this short wave radiation measurement from satellite. So you can see most of the places this correlation is now more than 0.6, 0.7, and it has improved almost everywhere. So this is the importance of this satellite derived OLR product, this short wave product. Now this is another product is upper tropospheric humidity. So by definition, this upper tropospheric humidity, because this water vapor channel is sensitive to a broad layer from 500 millibar to 200 millibar by this weight. So maximum contribution is coming from around 350 millibar, and then little contribution from 600 and 200. So this channel is giving you information about the relative humidity in a broad layer weighted by this weighting function. So if we compute UTH, so there is one relationship between UTH and brightness temperature in this water vapor band. So that we have derived one relationship for that. And now Kalpana, every half an hour we generate UTH product, that is the weighted average relative humidity in this layer. So these are the sample product for Kalpana 1 UTH, every half an hour product. You can see the scale here. But the only limitation is that when you have deep cloud, when cloud is penetrating deeper than this layer, when clouds are in this layer, lower atmosphere, then there is no problem because sensor is not sensitive to those clouds. But when the cloud penetrates above this level, then we will not get that relative humidity measurement. So these are the regions where we have deep clouds and we do not retrieve UTH values over these regions. And these are the validations of UTH derived from Kalpana with the UTH computed from radio sonde observations. So this is Kalpana versus radio sonde, and this is Meteosat UTH versus radio sonde. So our product works better than the Meteosat product, slight better, because our satellite is concentrated over Indian region. Pardon?
What is the resolution at which you are generating this product? UTH and all?
Yeah.
Horizontal resolution.
Horizontal 8 kilometers. Yeah, every picture. But it is every 8 kilometers, but to remove the cloud, we are using surrounding 5 by 5 pixels. So 5 by 5 pixels, based on 5 by 5 pixels, we remove the cloud, and then if it is not cloudy, if it has only low level cloud, then we compute UTH based on this relationship. And now this similar to OLR, this also is very good tool, very good parameter to validate the model for the diagnostic purpose. This can be assimilated also in model, but we have to take care of that weighting function, that it has to be assimilated according to the weight given by the weighting function. But if you compare, if you have a model field of relative humidity and you compute UTH based on the weight given by that function there. So this is the UTH computed from Kalpana, observed from Kalpana, and this right side you can see that this is INSAT analysis. So the UTH which is computed from INSAT analysis. So this way you can even validate the quality of the analysis and as well as the quality of the forecast. So if you run your model, like Prashant has done this experiment, he has run model for during the summer season, and he found out what is the RMSD in 6-hour forecast and 18-hour forecast, 12-hour forecast and 20-hour forecast, 2-time forecast. So he did a continuous assimilation from say 1st June to September, 12-hour forecast and 20-hour forecast. For every that forecast time we have UTH from Kalpana. Now he found, he computed UTH from model, forecast field, and we have UTH from satellite. So found out the bias and RMSD, and they are plotted here. So this way you can see how well your model is working for 12-hour forecast and 24-hour forecast. So this is just I am showing an example how you can do the diagnostic of the model forecast for relative humidity. So this is another product, that is sea surface temperature. This is a very important boundary parameter for different models. Right now we have only single channel, this thermal infrared in INSAT-3D and Kalpana. So because this requires some water vapor correction to arrive at accurate estimation of SST. So that water vapor information we are taking from global forecast, and then we developed an algorithm where from thermal infrared radiances we can compute SST. So this is one monthly composite of SST. Daily composite you will find lot of cloudiness, you will not find that good image, but just you can see here this monthly composite sea surface temperature from Kalpana. But in future, because we have now INSAT-3D planned for next year, INSAT-3D will have a, in VHRR, it will have one split channel from 10 to 12 micron. One of those channel is more sensitive to the water vapor. So by getting the information of water vapor from the difference of these two observations, we can correct that water vapor. So then in that case, we will not need water vapor correction from model forecast. Because here model forecast error of water vapor will also give some error in the SST. And these are the rainfall estimates from INSAT series of satellites. So this also again we can use for the diagnostic purpose, for validation of the rainfall forecast of your model. So these are two different type of rainfall product which we derived from Kalpana. This is actually large scale, large spatial as well as temporal scale, average scale rainfall product, MGPI. And here we use GFS, relative humidity, and TPW, total precipitable water, for correction in the this rainfall estimation. And this is another product, we call it INSAT multispectral rainfall analysis. So here these INSAT observations are calibrated with microwave radiometers, and those calibrated coefficients are used in INSAT, and we get very high spatial as well as temporal resolution product for rainfall. So these two are different products. If you want to validate or compare your model in the daily or weekly time scale over large area, this product will be better. And if you want to validate, say, for meso scale, so you can validate with this type of products. And these are the products which can be used for diagnosis or which can be used for assimilation. But another thing is the direct radiance assimilation. So even our colleague have used this Prashant and his colleagues, they have used Kalpana radiances in water vapor and thermal infrared to assimilate in the WRF model, and they found that these are the impact parameter. So all these red colors, they show positive red, and these colors, they are the positive impact. So most of the regions you will find that it is having positive impact on the forecast. So this is just one sample of that radiance assimilation. Now, these were the first generation satellites which India has launched in geostationary orbit. Now the second, this next series, INSAT-3D. So this will have a much more advanced sensor. First time we will have a sounder, 19-channel sounder in orbit, which will give a vertical information of temperature profile and humidity profile, which right now only US has in the geostationary orbit. Other countries having in polar orbit like NOAA, HERS, or this NOAA series of satellites, they are in the polar orbit. But geostationary orbit, we have only US which is having that satellite in orbit. So we will have 6-channel imager. This channel, and this channel is similar to Kalpana, but now we are adding one split window here to correct the SST information for water vapor. And we are adding one more channel here. This is a mid-wave infrared. This channel is very, very sensitive for changes in the temperature. So we can retrieve surface temperature information with better accuracy during night time. But daytime, this will have some solar contamination. So night time, we can get changes in the surface temperature information with the higher accuracy from this channel. And we are adding this one more channel here. This because we know that this is sensitive to the snow, ice. So the cumulus clouds or snow or ice detection, we can use this channel. And then we have a 19-channel sounder. These channels I will show in the next slide. So they are centered at these wavelengths from 14 micron. This is the CO2 absorption band. So these CO2 absorption band will give us the temperature information in the vertical temperature profile. And water vapor channels are here from from 7 to 6, and one more channel here because this is also sensitive to water vapor at lower layer. So these 4 channels will give us the water vapor profile in the atmosphere. We have one more ozone channel here. So this will provide the total ozone, column ozone in the atmosphere, and this will give us improved temperature profile during night time. So this will be the basically observation area for INSAT-3D. So if INSAT is placed here, we can only cover up to 60-degree zenith angle. So that 60-degree zenith angle will be here. So within this 60-degree zenith angle, the satellite has capability to monitor any area because this is sounder. It requires a large integration time. So this will be moving very slowly. So we have to select pure smaller region which is important for numerical weather prediction. If you want to do forecasting for cyclone, and if there is some cyclone over Bay of Bengal, you can focus sounder over this region, and get repeated coverage of profiles over this region only. Okay, so based on the application, based on the importance where you want to do the forecast, the INSAT-3D this sounder channel can be tuned and can get observations over those selected regions. So sounder products includes atmospheric profiles of temperature from surface to up to 0.1 millibar, that is up to 50 kilometer, then water vapor up to 100 millibar, and total column ozone, the surface skin temperature, and TPW and total ozone from this one. And these are just a spectral band of these different channels. So this way I will show that these are the weighting function for these different channels. So this basically shows that we are not getting observation from sounder in a thin atmospheric layer, but basically they are giving information in a thick, very thick atmospheric layers. So you can see this channel here gives information of this layer, broad layer, this gives information about this broad layer, and so on. These are the temperature sensing channel, these are the water vapor sensing channel for this layer, second layer, third layer, and fourth layer. So basically we are getting information from broad atmospheric layer, and from that we are reducing the atmospheric temperature and humidity profiles. And this is one sample, this is a gauge imagery. So this type of image will be obtained from INSAT-3D sounder, and that will be converted into the profile information. And these are our own, because we have developed a retrieval algorithm for temperature humidity profile from INSAT-3D, and these are the simulation results. So this is the temperature accuracy. Near surface we have RMSE of about 2K, and in most of the lower troposphere it is about 1K, and tropopause it is about 3K. So wherever we have inversion like surface or tropopause, their accuracy is not that good, but other places it is between 1 to 2K, and this is the accuracy of the humidity sounding. Now what these different colors show here is that though the INSAT-3D the resolution is 10 kilometer, one pixel is about 10 kilometer, so we can basically retrieve the profile at 10 kilometer resolution. But if we because sensor has its own noise, so if you use single pixel retrieval, our accuracy will be represented by this green line. This is single pixel retrieval. But if we use large number of sample to average, like 3 by 3 pixels, that is 9 pixels, or if we use 5 by 5 pixel FOV, so that will amount to degradation in the spatial resolution. But that will improve the profile information, because by adding many more pixels, more observations, you are reducing the random noise. If you reduce the noise, the profile this accuracy improves. So these are the different scenario when you want to use high spatial resolution, you have to compromise with the accuracy, and when you want to improve the accuracy, you will compromise with the spatial resolution. But fortunately with the INSAT-3D, there is one more provision, that if user demands that I want high spatial resolution, say 10 kilometer, and still I want better accuracy, then there are different mode of dwelling time. So sensor can, instead of doing fast scan, it can do slow scan, and that way it can improve the signal to noise ratio, and still you can get better accuracy with single pixel or with the better spatial resolution. But in that case, you will be able to scan only a smaller limited area. And these are the INSAT-3D imager products. So from these channels, now we can, again many of these parameters are similar to what we have seen from Kalpana and INSAT-3A. Only few additional parameters will be there. And accuracy of course will be better because we have many new channels here, like split window channel, the mid-wave infrared channel, and one short wave infrared channel. So this is the list of imager product. Basically, from importance I can say the atmospheric motion vectors, OLR, UTH, rainfall, SST. Now SST also is a primary product from this one. Cloud products, fog, snow cover, aerosol, and these are some of the research products from the satellite. Then, do I have time? Can I take 5 more minutes? Few slides, because these are the future geostationary satellites. These are the current satellites. So INSAT-3D is planned for 2013. And then, because we do not want that this satellite be there in orbit for 5-6 years and then we do not have any data. So for continuity, we have planned INSAT-3D repeat in 2015, and then geostationary hyperspectral sounder in 2012. And then these are few polar orbiting Indian satellites. OceanSat-1 was launched in 1999, which had a multi-scanning microwave radiometer, MSMR, and OCM. Then OceanSat-2 was launched in 2009, which has a scatterometer and radio occultation sounder. The SARAL is a joint Indo-French mission. This will be launched in 2011. This is altimeter. And Megatropic mission, this is again a science mission jointly with the French agencies. So this will have microwave imager, microwave sounder, this radiation budget scanner, and again this radio occultation sounder. So MSMR actually was again an important satellite, though it worked only for 3 years, but it provided very valuable information in terms of many applications. So it was having 6 gigahertz, 10 gigahertz, 18 and 21 gigahertz. So it provided very similar observation, similar to Nimbus SMRR. So one of the products, soil moisture, which we assimilated in the model, because this is a study by Koester in Science, which shows that soil moisture is has very sensitivity to rainfall prediction in these regions where you see the red color. These are the hot spots. So India is one of them. So if we can provide better estimate of soil moisture as a boundary condition, we can improve our predictability of the forecast. So this was one experiment done by us when we assimilated MSMR derived soil moisture in the numerical weather prediction model, and we found that when we compare with the this INSAT analysis, this was control run, and this was the run with the MSMR derived soil moisture. So this, because it was simulating very high rainfall over few places, whereas this was not present in the INSAT analysis. So when we assimilated MSMR, this became very similar to the INSAT. So this was only few studies done. It was not we need a large study to reach any conclusion, but the positive impact was seen by including satellite derived soil moisture in that. So these are the few samples of soil moisture from OceanSat satellites. Now we do not have a microwave sounder on microwave radiometer on any of our polar orbiting satellite. So what we are doing is we are using our algorithm to derive soil moisture product from this other satellite, like AMSR is there. AMSR is having 6 and 10 gigahertz. So we derive using our algorithm the soil moisture over Indian region and compared with the NASA products. And we found that our products are better than those available from NASA product when we compared with this observations, ground observations over Indian region. So this type of data set can be useful for boundary condition over Indian region, particularly for the mesoscale models. This is OceanSat-2, which was launched in 2009. So this has scatterometer and OCM. I think Prashant had made yesterday some presentation about this. So from this you can get sea surface wind vectors. So this is in continuation to the quick scatterometer. Now this is providing global information on sea surface winds for basically for surface wind speed. And this is a Megatropic science mission, which will focus only over thin tropical region. This will have a Saphir, a microwave sounder. And this is Scarab for Earth radiation budget, and Madras. This is a radiometer, microwave radiometer for temperature, and Rosa, radio occultation sounder for temperature and humidity profile. So these products will be available from Megatropic. And this is SARAL Altica. This is again a joint India and French mission. And this is altimeter for sea level topography. All these data which is derived from Indian satellites are estimated by our algorithms. We keep on these two websites. So this website is developed by SAC, Space Applications Center at Ahmedabad. So www.mosdag.gov.in. And this is maintained by National Remote Sensing Center, Hyderabad, NRSC. So these two are the basic our website from where you can get these satellite data. So most of the science mission data we can get like SARAL, Altica, Megatropics, INSAT, SARAL, INSAT, Kalpana. Those data you can get from MOSDAC. Few of the satellite data you will obtain from NRSC. Thank you. Rainfall. Yeah.
Pictures,
Rainfall is derived from that. Yes. See, this basic, it's indirect measurement. Like assuming that if you have a cloud, tall clouds, like some empirical relationship. If you have clouds at brightest temperature of 230 K, or say certain height, suppose 5 kilometer, 6 kilometer. So by empirically they have measured that if you have this much area covered by a cloud which is having brightest temperature less than 235, this will be the rainfall corresponding to that. This is the empirical formulation. So simply you take 100 by 100 pixels or 100 kilometer, 100 kilometer, count the pixels where brightest temperature is less than 235 K and find out the fraction. So suppose your fraction is 60%, 0.60. So multiply 0.60 by that empirically derived parameter, and then we get the QP. That is called quantitative precipitation index. But this is reliable on longer time scale and longer spatial scale. But our colleagues at SAC, we have developed, because that was only QP, we call that QP. This is MGPI, modified GPI. So here, how do we modify? Because sometime even 235 may not be raining. Sometime even 250 may be raining. Depends upon orography. So what we do, based on forecast model, you take some parameter from forecast model, like water vapor, humidity, total percentage water, and wind fields, and then based on that you provide some additional parameter there. So that will do the adjustment. That will do that adjustment in the QP. So that we call as modified precipitation index. And the other methodology, in that what we do is, because microwave radiometers or microwave radars, they give very accurate information of rainfall. So if we have simultaneous pass of say INSAT satellite and microwave satellite, so that time you use for calibration. So if this is my cloud picture and this is giving this is brightness temperature, at the same time what was the rainfall estimated by the microwave sensor. So from that we calibrate the rainfall from INSAT pictures. So that is called another method, IMSRI. So there are two different approach. One is using forecast to correct the QPE, and other is using microwave observations to correct for this rainfall.